So we were discussing about this one in the last class, that is a problem. Okay, so problems we were discussing in the last class. See this question: iron bar falling through a hollow region of thick cylindrical shell made of copper experiences a retarding force. What can you conclude about the nature of the iron bar? Okay, an iron bar is falling through a hollow region of a thick cylindrical shell made of copper. Experiences a retarding force. That means it is not falling down easily. It is facing some retarding force. What may be the reason? Can anybody explain? Can anybody
iron bar
explain?
experience an opposing force.
There is a hollow cylinder, something like this, and they say that iron bar is falling. Okay, hollow region of thick cylindrical shell made of copper experiences a retarding force. What can you conclude about the nature of the iron bar? Iron bar nature of the iron bar. This is iron bar.
Iron bar magnet.
Yeah, magnetarium. So it should be magnet, because when it is falling down, it will develop a change in the magnetic field lines associated with the metallic cylinder. So an EMF will be induced in it, and there will be back EMF, isn't it? So it is another application of Lenz's law. Induced EMF, current opposes its cause. Current opposes its cause, so they develop a kind of retarding force. So that is the reason why it develops a kind of retarding force. Now you see this next slide, motional EMF. You may be remembering motional EMF when a conductor is moving in a magnetic field. See this one, when a conductor is moving in a magnetic field. This is moving in a magnetic field with a velocity v. A conductor is moving in a magnetic field with a velocity v. Then an EMF is induced between the ends of the conductor, that is called motional EMF. Okay, conducting, see here, a conducting loop with a movable arm or side inside a magnetic field. So this is a conductor which is moving in a magnetic field. Now let's see, let L is the length of the conducting rod, V is the velocity of conducting rod, then B is the magnetic field present there, X is the length of variable side. That means a small side. Let us take a small side X here. Okay. Now we know that flux is equal to B dot A. B dot A, that is BA cos theta. BA cos theta. Here the angle between B and A both are in the same direction. Magnetic field is inward. Area vector of this loop is again in the same direction. So theta is 0. So it is B multiplied by A. So what is A here? A is equal to L multiplied by X. So this area, this small segment area, this is L, the length of the conductor, and X is the small distance which is moved by the conductor. Okay, L is the length of the conductor and X is a small distance moved by the conductor. So we can say that the area changed there is L into X. Then from Faraday's law of electromagnetic induction, we can say that E equals negative d phi by dt, d by dt of B Lx, d by dt of phi. Phi is equal to B dot A, and that A we converted into L into X. So that is d by dt of BLx. So B and L are constants because B is fixed magnetic field, L is the fixed length of the conductor. The only variable there is X varies with the time. When it is moving from one side to the other side, X varies from this one, 0 value to the maximum value. X varies from a 0 value to maximum value. All the parameters remain same. So here we can write it as dl dx by dt. The dx by dt we know velocity. Dx by dt is the velocity. So we got the relation E equals BLV. This EMF is called motional EMF. Motional EMF. So by the name motional EMF, we mean that there develops an EMF between the ends of the conductor when the conductor is moving in a magnetic field. There develops an EMF between the ends of the conductor when the conductor is moving in a magnetic field. So that is called motional EMF. So we can derive the motional EMF from Lorentz force also. Okay. So we are trying to move the conductor or a rod of length L with a velocity v. A rod of length L is moved in a magnetic field with a velocity v. See that one? V magnetic field, v is the velocity of this one, then Q charge, then E the electric field. See this one? Then the induced electric potential is taken as V. V is the induced electric potential. Then from Lorentz force, we can write it as Fe equals QE. FB is Q into VB. Q into V cross B. You may be remembering this. FB is equal to Q into V cross B. V cross B. Okay. So when a conductor of length L is moving in a magnetic field, there develops an EMF between the ends of the conductor. See this one, V equals E multiplied by L. So V equals BLV. So B is the magnetic field, A is the length, and V is the velocity. Then the current can be taken as current is the ratio of voltage to resistance, then BLV divided by R. So this is the induced current due to motional EMF. Induced current due to motional EMF is BLV divided by R. Then we know another equation F equals IL cross B, that is the force experienced by a current carrying conductor placed in a magnetic field. Force experienced by a current carrying conductor placed in a magnetic field, that is IL cross B. Because B is a constant, so we can take it outside. So BIL sine theta, angle between L and B is 90, so it is BIL. So instead of I, we can write BLV by R. I can be taken as BLV by R. So when we substitute it, we get BL multiplied by BLV by R. We get the final value for the force as B square L square V by R. B square L square V by R. Remember, this equation starts with F equals IL cross B, Fleming's left hand rule. F equals IL cross V. Then we can substitute the value of I as BLV by R. We get the equation for the force as B square L square V divided by R. This is the force on a conductor moving in a magnetic field. EMF developed across the ends of a conductor is BLV. Then the force on the conductor when it is moving in a magnetic field is B square L square V divided by R. Then the power can be taken as the product of force and velocity. Force multiplied by velocity is power. So force equation we know B square L square V by R. When you multiply it with another velocity, you get the equation for power. Power is B square L square V square by R. This is also a kind of generator, you see. The slide rail generator. Of course, this we don't have enough syllabus. Somebody's mic is on. Whose mic is on? Bijan, please mute yourself. Okay, so this is called a slide rail generator. Because when you're moving a conductor in a magnetic field, there will be EMF developed across the ends of the conductor. So we can use this phenomena for developing EMF or producing EMF. Such an arrangement is called a slide rail generator. Somebody's mic is on, please switch it off. See, this is a mechanism there. We can use it for the production of EMF. We have to move a metallic conductor in a magnetic field. So there must be a rectangular frame and a conductor which is moving in a magnetic field. So if it is moving with constant velocity, we can develop EMF at a constant rate. It is called a slide rail generator. See, this is the variation of flux and EMF when a rectangular frame is moving through a magnetic field. Rectangular frame is moving through a magnetic field. This is the variation of flux as well as EMF. See, you have to remember one thing. Whenever there is a change in the flux associated with the coil, there will be an EMF induced in the coil. But if the coil is already inside the magnetic field and moving inside the magnetic field, there is no variation in the flux. So in such cases, induced EMF will be zero. Whenever there is a change in the EMF, change in the flux linked with the coil, EMF will be induced. So that is the idea we have to remember here. See this one, up to this, it is constant, and from here, say, from here to here, there is no EMF. From this point to this point, there is no EMF. You can closely watch that. From this point to this point, the flux linked with that one is fixed. There is no variation. If there is a variation for the flux linked with the coil, there will be EMF. See this one, another illustration. See, this rectangular frame is entering into the magnetic field. Entering into the magnetic field, three concepts are plotted in the same plane itself. First one is flux, BLB. Then this is EMF. See here, there is no flux. When it is moving from this point to this point, flux increases to maximum. And from this point to this point, no variation in flux, means no change in flux, no change in flux. So no BLV, there is no EMF. Okay, there is no EMF from this point to this point. Okay. Loop, this is a case where the loop is moving in. Here the loop is already out. Here the loop is already out. No moving in or no moving out. No flux, no EMF. Here the loop is moving into the magnetic field, so there develops an EMF. Okay, so here it is moving in the constant flux, so no EMF. See, so no EMF is there from this point to this point. EMF is zero. See, okay. Again from this point, the loop is coming out. When the loop is coming, can you hear me?
Yes, sir.
Yeah. When the loop is coming out, from the magnetic field, again there develops EMF. You see, but in the opposite direction. Initially, EMF was negative. See, EMF was negative, minus BLV. EMF was negative, and from here to here, no EMF, and from here to this point, and from this point to this point, again EMF is there. That you have to remember. So the point you have to remember here is, the concept you have to remember here is, whenever there is a change in the flux linked with a coil, an EMF will be there. And if there's no change in the flux linked with the coil, EMF won't be there in the coil. So that is the only thing you have to remember. Between these two areas, you see flux is there. Flux is there, full flux is there, but there is no change in flux. It is already inside the magnetic field. No change in flux is there, so no EMF. Okay. Now let's see this problem. A square loop of side 10 centimeter with its side parallel to x and y axis are moved with a velocity of 8 centimeter per second. In such cases, immediately you have to convert that centimeter per second into meter per second. So 8 centimeters per second. How will you convert it into meter per second? You see here, 8 into 10 power minus 2 meter per second. Okay. Then loop of side 10 centimeter. So one side is 10 centimeters, 10 centimeter. That is 10 multiplied by 10 power minus 2 meters. 10 into 10 power minus 2 meters. Field is non-uniform and has a gradient of 10 power minus 3 Tesla per centimeter. What does it mean? Tesla per centimeters. dB by dx. dB by dx is equal to 10 power minus 3 Tesla per centimeter. Okay. Calculate the EMF induced. Let's see how can we calculate the EMF. EMF, as per basic equation, EMF is minus d phi by dt. Okay. Phi equals, we know phi equals B dot A. Then d phi by dt equals d by dt of B dot A. Okay. Then minus A into dB by dt. Then dB by dt we can convert like this. dB by dt we can write like this. dB by dt equals dB by dx multiplied by dx by dt. dB by dt equals dB by dx multiplied by dx by dt. So we have the value of dB by dx. dB by dx is there. Then the dx by dt. What is the dx by dt? It is nothing but dx by dt. It is nothing but velocity. It is the velocity. So we can substitute all the values and we get the result as 8 into 10 power minus 5 volt. Either we have to convert all these into meter per second, or we have to keep everything in centimeter per second. Either meter or centimeter. If you are taking meter, everything should be in meter, and if you are taking centimeter, everything should be in centimeter. See, there are two terms here. One is dB by dx. If you take dB by dx in Tesla per centimeter, there you have to take velocity also in centimeter per second. And if you take dB by dx in Tesla per meter, here again velocity you have to take it in meter per second. Okay, let's see next. So here the question is, a figure shows a rectangular inducting frame MNOP of resistance R placed partly in a perpendicular magnetic field, moved with a velocity v. Obtain expression for the force acting on the arm ON and its direction. Power required to move the frame. See this, how can we solve it? Induced EMF is, as usual, induced EMF is BLV. Then the current we can write it as EMF divided by R, that is BLV by R. Then the force is as per Fleming's left-hand rule, force is BIL, or IL cross V. So V square L square V by R. This we have already seen. Okay, then the power is force multiplied by volume. Power is force multiplied by volume. Then sorry, force, not volume, force multiplied by velocity. This V is velocity here. Force multiplied by velocity. So B square L square V divided by R. Square V square divided by R. Now another question. A rectangular frame of wire is placed in a uniform magnetic field directed outward. AB is connected to a spring. How the induced EMF in the coil would vary. Okay, so how can we solve this? Let's see. So it will oscillate in a simple harmonic way. Expression for the displacement we can take it as Ex cos omega t, because there is a spring. When you when you pull it and release, it will go back and forth motion. That is simple harmonic motion. So A cos omega t. Then flux of phi equals basic expression for flux of phi is B dot A. Then L is the length AB. Length AB is L, and the small displacement here is delta x. Okay, so L into delta x we can take, or Lx we can take. Then d phi by dt, then we have to go for BL omega sin omega t. BLA omega sin omega t. That means it executes simple harmonic motion. Only the concept here is flux, you know, the value of flux, you know, then area you have to find it. Normally in all cases area will be equal to L into breadth. So because it is a rectangular frame, but here this B small breadth will be, you have to take it as small displacement delta x. Then you have to take the d phi by dx. So that is a step. Okay. The small displacement in the x-axis you have to take, then you have to take the d phi by, means the variation of that displacement with respect to time. Then you will get the equation for EMF. Another question. Now here this is another typical problem. Aeroplane is flying horizontally from west to east with a velocity of 900 km per hour. 900 km per hour. That is 900 multiplied by 1000 divided by 60 into 60 meter per second. Calculate the potential difference developed between the ends of its wing having a span of 20 meters. Span of 20 meters, that is L is equal to 20 meters. The horizontal component of Earth's magnetic field is 5 into 10 power minus 4 Tesla. VH is equal to 5 into 10 power minus 4 Tesla. Let's see how can we solve this. E is equal to BLV. When we get the velocity 900 km per hour into meter per second, we get 250 meter per second. Okay. The wingspan, that is L equals 20 meters. Then the vertical component we have to find out. Horizontal component is given. Horizontal component of Earth's magnetic field is given. It is 5 into 10 power minus 4 Tesla. And the angle of dip is also given as 30 degree. We know that BV divided by BH is equal to tan delta. So BV equals BH tan delta. Okay, vertical component will be equal to horizontal component multiplied by tan of the dip angle. So you get the vertical component. Then by using this equation BLV, E equals BLV relation, we can find out the voltage as 1.44 volt. Is it okay? Now another problem, a conducting rod of length L is kept parallel to a uniform magnetic field B. That is moved along the magnetic field with a velocity V. What is the value of EMF induced in the conductor? Let's see how to solve it. See, equation for force is, see the second question. Equation for force is BIL. Remember, I current is BIL, BLV divided by R. EMF divided by resistance is current. EMF equation is BLV divided by R. And the force equation is, we can find out the value of force here. Force BIL. So I we can substitute as BLV by R. So V square VL square divided by R. We can find out the value of force. Then if we know the value of force, then power is force multiplied by velocity. So these things are very easy. You have to remember this equation BLV. Then E equals BLV equation. This is equation 2. Then force is this one, BIL equation. Then power is equal to force multiplied by velocity. This is equation 3. Force multiplied by velocity, equation 3. So these are the simple things you have to remember. By using all these, by using these simple equations, you can attempt any question. Okay, another question. See this one. When a conducting loop of resistance 10 ohm and area this much, resistance is 10 ohm and area is this much, is removed from an external magnetic field. Variation of induced current in the loop is shown in the figure. Total charge passed through the loop, change in the flux, magnitude of magnetic field applied. See this. Total charge. Charge is equal to, see this is current time graph. So area under the current time graph is charge. Area under the current time graph is charge. Just take the area under this graph. It will give us Q. So it is 0.2 coulomb. Like that, you can see we can do all these things. It is very simple thing. If you know all these basic equations, it is very simple. These are all the previous CBSE questions.